the mathematics behind bending moments. Welcome to this short yet insightful dive into the mathematics behind bending moments. You might have heard about bending moments in structural analysis, but today we'll break it down into simple terms. By the end, you'll understand the basic mathematical principles that govern how forces cause bending in beams. Let's jump right in. What is a bending moment? A bending moment occurs when a force is applied to a structural element, like a beam, causing it to bend. Think of a diving board. When a person stands on the edge, their weight creates a force that makes the board bend downward. Mathematically, a bending moment is calculated as the force multiplied by the distance from the point of force application to the point of interest. It's often expressed as m equals F times d, where m is the moment, F is the force, and d is the distance. The moment equation explained. Let's break that equation down. The moment is measured in Newton meters, meaning the force in newtons is multiplied by the distance in meters. The distance, also known as the lever arm, plays a critical role. If the force is applied further away from the support, the bending effect is greater. Picture this. If you push on the middle of a beam, it bends less than if you push at the end. That's the lever arm in action, controlling the intensity of the bending moment. Understanding the sign convention. Now, bending moments aren't just numbers, they have direction, too. Engineers use a sign convention to keep track. Positive moments cause what we call sagging, where the beam curves downward. Negative moments cause hogging, where the beam curves upward. This helps when analyzing different points along the length of a beam, as forces might create different effects at different locations. The importance of bending moment diagrams. To visualize how moments change along the beam, we use something called a bending moment diagram. It shows how the bending moment varies with the distance along the beam. Peaks in the diagram indicate areas of maximum stress, where failure is more likely to occur. Understanding the mathematics of bending moments helps engineers design beams that can withstand these stresses. In summary, bending moments tell us how forces cause beams to bend, and the simple equation of m equals F times d helps us calculate these effects. The lever arm, sign convention, and bending moment diagrams are key tools for engineers when designing safe and reliable structures. Thanks for joining me in this quick exploration into the mathematics behind bending moments. Welcome to Blueprint to Reality. In today's episode, we're diving into some of the most shocking building collapses ever caught on camera. While we often take the stability of structures for granted, engineering failures can lead to sudden and catastrophic collapses. These events are rare, but when they happen, the footage serves as a stark reminder of the importance of structural integrity and design. Let's take a look at 3 of the most unforgettable building collapses ever captured on film. Sampoong Department Store Collapse, South Korea, 1995. Our first collapse is the Sampoong Department Store in Seoul, South Korea. In June 1995, this 5-story luxury department store collapsed during business hours, killing over 500 people. The shocking part? The collapse occurred in just 20 seconds. The footage shows the entire top floor buckling before the structure crumbled inwards like a house of cards. What went wrong? Investigations revealed that illegal construction modifications were made to the original design, weakening the building's support columns. This tragedy serves as a reminder of the dangers of cutting corners in engineering and construction. Hard Rock Hotel Collapse, New Orleans, 2019. Next, we have the Hard Rock Hotel collapse in New Orleans, which was under construction when tragedy struck in October 2019. Footage captured by nearby witnesses shows part of the upper floors collapsing onto the floors below, eventually sending a massive cloud of dust into the street. In this case, design flaws and improper load distribution were the main culprits. The collapse claimed 3 lives and sparked a massive investigation into the project's management and construction practices. Seeing this happen in real time emphasizes how crucial oversight and safety protocols are, especially in large projects. Surfside Condo Collapse, Florida. The Champlain Towers South collapse in Surfside, Florida, is one of the most recent and devastating building failures caught on camera. On June 24, 2021, part of the 12-story condominium suddenly collapsed in the middle of the night while residents were sleeping. Security footage shows the building crumbling in 2 stages, with part of the structure collapsing and moments later, the remainder falling down like dominoes. The collapse led to the deaths of 98 people. Investigations pointed to years of structural degradation, particularly in the foundation and concrete slabs, which were exposed to saltwater corrosion. This incident has since sparked a nationwide reassessment of building safety standards and inspection practices. Key lessons from these collapses. What can we learn from these tragedies? While each collapse had different causes, whether it was poor design, construction flaws, or a lack of maintenance, there's a clear takeaway. Building safety is non-negotiable. Cutting corners on materials, ignoring maintenance, or overlooking design flaws can have devastating consequences. Engineers, architects, and builders play a critical role in ensuring the long-term stability of every structure. These building collapses serve as harsh lessons in the importance of engineering, design, and safety inspections. The footage might be shocking, but it also reinforces the need for continual innovation and responsibility in the construction industry. Thanks for watching Blueprint to Reality. Don't forget to like, subscribe, and hit the notification bell for more insights into the world of civil engineering and structural design. Stay safe, and see you next time. Welcome to this short yet essential discussion about the impact of torsion on building stability. You've likely heard of forces like bending and compression, but today we're focusing on torsion, a twisting force that can cause significant problems if not properly managed in structural design. In the next few minutes, we'll explore what torsion is, how it affects buildings, and why engineers must consider it to ensure structural stability. What is torsion? Torsion occurs when a structural element, such as a beam or column, experiences a twisting force around its axis. Imagine twisting a dish towel by holding both ends and rotating them in opposite directions. That twisting motion is torsion. In buildings, torsion can be caused by uneven distribution of loads, wind forces, or even seismic activity. When torsion affects a structure, it can lead to significant instability if not properly accounted for in the design. How torsion affects building stability. So, what happens when torsion affects a building? If a structure experiences twisting forces that it wasn't designed to handle, components like beams and columns can deform or even fail. Torsional forces are particularly dangerous in tall, slender buildings or irregularly shaped structures, where the center of mass may be offset from the center of stiffness. This mismatch can lead to uneven twisting during events like high winds or earthquakes, creating dangerous stress concentrations in parts of the building. Torsional irregularities and their dangers. Torsion is especially problematic in buildings with torsional irregularities, meaning the structure isn't symmetrical or balanced. For example, if a building has a large, open area on one side and heavy, rigid walls on the other, it may twist more under certain forces. This uneven twisting can amplify stresses in parts of the building, leading to cracks, fractures, or even collapse. Engineers must design structures to minimize torsional irregularities by carefully placing walls, supports, and load-bearing elements to resist twisting forces. Engineering solutions to control torsion. So, how do engineers prevent torsion from compromising building stability? One solution is to ensure symmetrical design, so forces are evenly distributed. Another is to use elements like shear walls, bracing, or torsional dampers to resist twisting forces. In earthquake-prone areas, special attention is given to torsional effects, as seismic forces can cause extreme twisting, putting buildings at risk. By designing with torsion in mind, engineers can make buildings that remain stable even under challenging conditions. In conclusion, torsion is a powerful force that can severely impact a building's stability if left unchecked. By understanding how torsional forces affect structures and using smart design strategies to control them, engineers can ensure that buildings are strong, safe, and capable of withstanding twisting forces caused by wind, seismic activity, or uneven loads. Thanks for joining me today, and remember, structural stability isn't just about strength, it's about resisting every force, including torsion.